Okay, Assalamualaikum warahmatullahi wabarakatuh. Good morning, everyone. We are now in the last week of this semester, and this is the last meeting for this course and also this 3-in-1 program for Dr. Aizzat. I hope that we will continue cooperate after this, and
Inshallah.
I hope also some of you could visit Dr. Aizzat's place in the future.
Yeah,
Uh,
fully.
okay, without further ado, please, Dr. Aizzat, time and screen is yours.
Okay, thank you, Dr. Dimas. Let me share my screen. Can you guys see the screen?
Yes, Doctor.
Okay, thank you. Okay, Assalamualaikum, and for me it's good morning. Also, good morning in Indonesia. Today will be our last topic and our last lecture. I'm very happy to teach you guys, and I'm really excited. And if you have any question, you can always ask me, not after during the lecture. Also, you can email me or text me if you have a further question. No problem. Yeah, I hope that we can always collaborate with Dr. Dimas after this. So the topic for today's lecture is the robots kinematics and motion. So actually this topic, we need a few other lectures, but I try to give some a brief mathematical overview, not so in detail, but if you see that there's a lot of mathematical equation, just please ignore it first, because I want you to see the concept. The concept is the most important thing that I need you to understand. That's why in the last lecture, I give to you some simulation example whereby you need to simulate the movement of the robot. You can see that there is some movement of the robot, there is some trajectories. And for today's topic, we are going to see how what is behind these robots or this simulation development. So the mathematics behind it, so that when we want to replicate the same thing like you did in the Python simulation, the code that already given to you, you can do the same. So this is the topic. And in fact, this topic is really important if you really want to master the control system subject for the mobile robot navigation, because this topic will show you the basic on how the robot move. So today we are going to cover several overview of differential or several drive type. We call it a robot drive type, whereby you have a differential drive type, tricycle, or omnidirectional type, synchronous drive, command, and steering drive type of the robotic system. So we start with the first kind of the drive type. What we call it, I think this is the most common one. What we call it differential drive type. So the differential drive type, this robot is consists of two fixed powered motor wheel. Means that we will have two motor inside the tire or outside, but you can control it independently. The left and right side of the robot platform, the two wheels are independently driven. One or two passive cursor wheels are used for balance and stability. Means that you will have two motor and maybe at least minimum one caster, so that your robot can be balanced. And this is the simplest mechanism, mechanical drive, since it does need rotation of a driven drive. So we don't need a steer drive. So we only need two tire only. So this is the concept of the differential drive. So if we draw it in this kind of robot, you can see that we have, in order to control the motion, you can have the A, B, and C kind of motion, whereby this is where we put the motor or inside the tire. So if we give the same magnitude for each of tire, you can create a straight motion. But if you give, for example, on the right side of the tire in this slide, and the left side is higher, you can create a left motion. So this is how we create a turning. And if we reverse the polarity like this, you can create circle, but the circle is not at the center of gravity of the robot. It's at the center of the axle between these two tires. So that's why you can see that this is the circle rotation of the robot. Because some people confuse that if we make a circle, they assume that the circle is at this part. But in actual cases, for the differential drive, the circle is driven by this kind of two things. So you can see that on the D, this is how the differential drive movement. So they don't have parallel parking or this kind of thing. So this is the most configuration of mobile robot because of the flexibility of the control and the what we call it, the easiness when we want to program it into our control system. And by using a differential drive system, actually we can predict its motion. So if you see on the previous slide, we know that by changing the value of the left velocity and right velocity, you can achieve some turning, right? But the question is, how much turning do we want? So by understanding the kinematic or mathematical properties, because when I say kinematic, we try to predict the motion of a particle, the motion of a robot inside a plane, so inside a X and Y axis. So when you see on the slide here, we can estimate the curvature or the radius of the robot that is having what we call it in differential drive configuration. For example, you can see here in the slide here, you can see that if this is the robot's relationship, you can see the R of the radius here. If you rearrange the radius, you can see that you will have relationship between you can achieve the relationship between left and right velocity of the robot, and A is the robot's parameter, means that your robot's dimension. So when we know the velocity of left and right tire, normally when we apply into our robot, we will send it using speed sensor, right? Like odometer, encoder. So this speed sensor will give you the value of left and right. So in this case, if I'm using a robot type with differential drive configuration, I need to have at least 2 speed sensor, left and right. If I have 1 speed sensor only, I'm not able to predict the motion of the robot. So means that if I have 2 speed sensor, I'm using this equation, I will be able to predict the radius of the robot's motion. So you can see here when we have VL over VL equal to VR, you can see from this equation, the divider on the bottom side becoming a 0, then you will have R is equal to infinity. What is meant by this equation is if we have the R is equal to infinity, means that the vehicle will be traveling at infinity radius, means that it is at the straight motion. But when we prove this mathematically, but the problem when we program it, in the programming, you cannot divide by 0. Otherwise, your programming will crash. So you need to do something with your programmer, like if the value is the same, then it will come to go to other mode of control. So, but this is the general on how the kinematic of the differential drive mobile robot. And next we have 3-cycle motion. This drive has a single wheel which is both driven or powered and steered. So we only compared to the differential drive, if you see here, only have a single wheel, whereby the single wheel is driving and steering. Then for stability, 2 running unpowered wheel is at the back or front are used in order to have the 3-point contact required, because when you put your mobile robot on the base, you need to have at least 3-point contact on the ground so that the robot can become stable. So normally we will have 2 caster wheel for 3-cycle motion. The linear and angular velocity of the wheel are fully decoupled. For driving straight, the wheel is positioned in the middle position and driven at the desired speed. So if you see from here, this is the diagram of the 3-cycle motion of the mobile robot. So if you can see from here, compared to the differential drive, whereby this differential drive, you will have two independent motor at this part. But for the 3-cycle motion, you will have two motors at this part, means that this motor will be responsible for driving, means that front and back, and another motor will be responsible at the turning. So they are at the same contact point here. And for example, if I'm turning at 90 degree, I will have the C configuration. So means that this is the motor is being turned at 90 degree. And you can see that if I'm driving, I'm giving some driving value at this tire, you can see that the rotation is not at the tire. The rotation will be at the center of the Aizzat, similar like differential drive configuration. So this is the properties, although our motor is located at front. And differential drive, the properties of the differential drive and 3-cycle, we cannot perform parallel parking. This is the if the front wheel at its position is 90 degree, the robot will rotate the following the circular path at the center, in which the middle point of the railway is not in robot geometric center. Similar configuration with differential drive. Okay, so this is the configuration of the 3-cycle motion of the robot. So this is one of our project actually. So we try to make this forklift and autonomous. So if you see here, the forklift, actually the electrical forklift I'm saying about, there are different kind of forklift, but the forklift that we are using, maybe let me pause first. The forklift that we are using is using what we call it, a 3-cycle motion. So it's actually is an electric forklift. So if you see from here, there is a shaft over here connecting to this tire. So this tire can be used to control the drive. But you can see here, normally when we have electric forklift, the operator will control this steering, right? The steering, so that you can create a movement of your robot. But if you want to make this robot to become autonomous, right now we already have one single speed drive tire here. So what we do is we install one motor that is controlling the steering, and we replace the ECU inside here with our own controller. So this is the example of the 3-cycle motion. So if you see from here, when we install these two motion, you can see that the first, there is a caster wheel at the back. So this wheel does not have any motor here. So they just running freely, but we can control the what we call it, the drive and the steer at the same time using the back of the wheel inside here. Is that you have 1, 2, or maybe some will have 4 caster wheel, but one single wheel at this part. So this is the example of the 3-cycle forklift motion. And the next is we will have omnidirectional. So this drive can be obtained using 3, 4, or omnidirectional wheel. So using this omnidirectional, we call it, for example, this 4 mechanism wheel configuration. So this type of motion is the most flexible motion, whereby you can have a parallel motion. So if you see from here, you can see that we will have a parallel motion by controlling the value, the direction, the magnitude direction, and the vector direction of each wheel. So if we have on the left side, you have in the reverse polarity, and also in the right side, you are going outward from the vector direction. You can have left parallel motion, and you can have a turning that you want by having this configuration, and you can have a right parallel motion. So this is the most flexible configuration, but of course, this is the most complicated kind of motion for our robot. But normally, it's depending on the application that we use. For example, if we really need to design a robot normally this kind of parallel omnidirectional, we use it in the flat surface, and if we use it in the plan whereby the space is limited, that you need to have a parallel side motion. So this is the type of configuration. But if you have plenty of space, this type of, if you still choose this type of configuration, means that you are introducing more complex joint motion of your system. And the next part is the synchronous drive of motion. So the difference between from the previous motion is we will have a drive at the tire. We will have a drive at the tire here, but for the steering, you will have something like a mechanical linkage steering here. So if we rotate the steering, so these three steer will be steered at the same time. So this kind of configuration will ensure that you don't have any different in term of the steering value by having the some belting at your motor, at your tire. So this kind of configuration, we call it synchronous drive. The reason is, if you want an application that require a very precise angle for each of the robot's tire, you can use this configuration. But the problem is when we introduce a mechanical linkage such as a belt, the belt, you have to consider about the resolution of the belt. If you are using chain, the chain also have the minimum resolution. So if you want to have like an angle of rotation less than certain degree, you cannot have that because of the mechanical constraint. Also, if we are using belting, also we need to use, for example, some steering tensioner. This kind of mechanical complexity will be introduced, and it becomes more complex because you are trying to create an advanced system, and at the same time you have to deal with a mechanical problem. So this is the limitation of the synchronous drive. The next is also the most famous one also, whereby you have what we call it Ackerman steering. So this also kind of configuration that is being used in the mobile robot navigation. So normally we are using two kind of configuration. Either you are using a differential drive or Ackerman steering. The tricycle in the forklift motion also is not common. Normally they don't opt out with the tricycle motion. The Ackerman steering is the standard steering that is used in our car, in automobile. And some of the outdoor robot, for example, some of the agriculture robot also, they use this kind of Ackerman steering. It consists of two combined driven rear wheel, means that we have a driven rear wheel that is connected by one axle, and two combined steered front wheel. So we have one combined steered front wheel. Ackerman steering is designed to ensure that the turn of the wheel at all axles have a common cross point, which is, we need to understand the instantaneous center of rotation in order to predict the cornering. And also the Ackerman steering is also try to avoid the slippage, means that we want to avoid any slip. The Ackerman steering configuration, normally we will have a different value of the turning angle between left and right tire. But the difference in the turning angle between left and right tire is what we call it the Ackerman angle. So this difference of the angle normally is to cater to reduce the slippage when we take a cornering. But normally during the analysis, we try to simplify the difference between these two angles by having one simplified common angle. We try to assume that during cornering, maybe at the simple cornering, we assume that these two left and right front angle are the same, so that they have we can simplify these things so that we can use later in the analysis. So this is the limitation of the Ackerman steering. So the shaded area is accessible by the Ackermann steering robot, if you can see from the slide here. So if we want to go to this thing in one single motion, you cannot simply go like the omnidirectional wheel. So you need to have multiple kind of motion, like straight reverse, straight reverse, straight reverse, until you achieve this desired motion. You cannot simply directly go to here. And also on the right side. So this is the Ackermann robot limitation. So for tight space, the Ackermann robot is not recommended due to the limitation of the Ackermann. And next, we will have a skid steering configuration. This is a specialized implementation of differential drive and realized in the track in the form of bulldozer and armored vehicle. It's different from differential drive and increased maneuverability in uneven terrain. So maybe in the agriculture, for example, you have a very uneven terrain, you can opt out for this kind of configuration. And the higher the friction, which is due to its strength and the multiple contact point with a terrain, rough or even. So it's like an armor. That's why we can see that for military purpose, for the bulldozer, or in fact, if for example, tractors, right, or the future drive mobile robot for agriculture, they use similar contact point like the skid steering configuration, like to increase the contact with the uneven terrain. So I think for agriculture, maybe this is suitable for use. And right now we have seen that, okay, we have been through with the what we call it, sorry, we have been through with a lot of the configuration of the mobile robot. And right now we want to understand why we need to understand this kind of mathematical configuration. This is what we call is a mobile robot kinematic. So what is mobile robot kinematic? So the mobile robot kinematic, this will the configuration of the robot in our space. And we try to understand the relation of the robot with the its geometric parameter, with the robot size, and what is the constraint, what this robot can do is maneuver, what this robot cannot do, depending on the trajectory. That is why when I ask you to try your simulation, you can see that your robot move in certain kind of motion. They cannot have suddenly parallel parking. If you modify the coding, also you cannot have the parallel parking. You need to modify the mathematical model itself. So the kinematic equation depend on the geometrical structure of the robot. For example, if your robot can have different Cartesian, cylindrical, spherical, and articulated structure. So this is more on the robot arms kind of configuration. So this is just the introduction of the robot's kinematics. So normally, if we want to understand the motion, how our robot move in certain parameter, we need to understand these three kind of information. Actually, it's quite that topic, but I try to give an overview because it involves a lot of mathematical equation. So they will have direct and inverse robot kinematic, homogeneous transformations, and some constraint on the system. So for example, what is direct and inverse kinematic? Let's say you are creating a mobile robot here, right? This is your mobile robot, and you try to put some robot arm here on the mobile robot, and this robot arm try to do pick and place of your agriculture. For example, this is your trees, right? So if you see here, there are certain parameters that I have to control. The first is I have to control this the speed theta here. For example, let's say I have this theta 1, so I have to control this theta, and I have to control this theta, right? Then by controlling this theta 1, theta 2, and theta 3, I want to move my robot so that I can achieve at this point. I call it a P. I call it a point P so that I can do my operation in my robot workspace, so that I can do the pick and place. For example, I want to do the harvesting of tomato, right? So I can move my robot to go to the tree. So the question is, what is the value if I change the value of theta 1, theta 2, and theta 3 so that I can arrive at here? So this is what we call it a problem that we have to solve. We have two problems here, direct kinematic problem and inverse kinematic problem. So the direct kinematic problem is, let's say, I call it a direct kinematic. If I change my theta, means that if I change my theta 1, theta 2, and theta 3, what will be the position of the robot, right? So this is the direct kinematic problem that I have to solve. With that, I need to understand what is the mathematical equation that I have to derive inside my robot. So this is what we call it the direct kinematics problem. And next is inverse kinematic. Okay, so the inverse kinematic problem, if we compare with direct, for example, if I give certain value of theta 1, theta 2, and theta 3, maybe my robot will arrive at this location, at second location, which is from A to B. So if I change, so this is what we call, when we want to predict this thing, we need to have a math equation of the direct kinematic problem. But for the inverse kinematic problem is, for example, I want to go to this tree. I want to go to this tree whereby this tree have this point. For example, this tree is tomato tree, for example. So if my robot want to harvest this tomato tree, means that I need to know what is the location of this tomato tree, right? I need to know what is the location of this tomato tree, so that using the equation inside this inverse kinematic problem, this equation will help me to calculate what is the value of theta 1, what is the value of theta 2, what is the value of theta 3 in order to go to this location. So if we understand the geometrical properties of our robot, if we understand the technique that is involved when we want to derive, we can use this equation so that, okay, if I want to go to this point in order to do pick and place operation, I have to use this inverse kinematic so that my computer will give, okay, you want to go to this location, this is the value, and this value I will be sending it to my control system, and the control system will do the calculation so that it goes to the location that I want. So these two problems, direct and inverse kinematic problem, are related to each other. So I don't want to go in detail, but this is the idea that why we need to consider the direct and inverse kinematic of the robot when we want to control it. And also, this is some mathematical equation. Normally, when we do the forward and inverse kinematic, we try to represent the robot motion in terms of mathematics. So that's why you can see that from the diagram that I draw to you, normally we translate this diagram into a mathematical matrix, because this mathematics will be put into our computer for calculation. So we will have some matrices, some equation inside here. And kinematic is the branch of mechanics that investigate the motion of the material bodies without referring to their mass and or moment of inertia, or the forces I thought that produce the motion. And clearly, the kinematic equation does depend on the fixed geometry of the robot in the fixed world coordinate frame. So when we say that we are considering the robot kinematic, normally we will consider that the robot is moving at X and Y coordinate, and sometimes in the 3D coordinate space. So we will have X, Y, and Z. So we assume that our robot is moving into this space. And if you see this definition, we don't have any information on the mass, moment of inertia, and the force and torque that is required in applying this kind of motion that we want. But for a very heavy application, for example, I give you an analogy. When we are driving a car, right? When we drive a car and we drive at a very slow motion, maybe you are driving at 5 km/h, very slow. If you want to brake your car, you can immediately brake without anything happen. They can immediately stop at the point that you want. So this is what happening when you drive your car very slowly. But when you drive your car, a heavy car, for example, like a lorry, you drive at a very fast speed, for example, 80 km per hour, you drive a very big lorry, you try to stop immediately, you press maximum the brake, you can see that we cannot immediately stop the lorry, right? They will have some effect. This effect is called the initial effect, and the moment of initial effect due to the mass that is introduced to the body of your system. So because of that, we cannot rely on the kinematic alone if we have this kind of very fast and heavy robot, whereby we need to consider the dynamic as well. And also, in the robotic also we have a new term, what we call it Jacobian matrix. So normally you can see some mathematics here. I try to put it in a very simple way to explain. Normally, what is called by Jacobian kinematic is, let's say, let me put some. So if you imagine this robot, right? If you imagine this robot, so you will have a theta, you will have theta 2, and you have a theta 3. So if I differentiate this theta, right? If I differentiate this theta, so you can see that I try to predict the displacement. Where will be my theta will be moving. So if I have this equation, this metric equation inside here, I will be able to predict what will be a position. So I will be able to predict what will be the total position displacement that I will have. So by having this kind of prediction, I can predict that what will be the generate velocity of my robot, the generate position displacement of my robot. So this kind of displacement relationship normally will be expressed by what we call it a Jacobian metric. So this is some term that we use a lot in the mathematical. So this is the Jacobian metric also will have direct Jacobian and inverse Jacobian, similar like direct and inverse kinematic. So I don't want to go, but this is how we go into mathematical representation of the Jacobian of the robot. And the next is right now, just now we see that the differential drive robot configuration. I have shown to you guys that by having the understanding of the left and right positioning vector, we can do the differential motion. We can predict the radius. And in fact, you can see that, for example, if the position of the robot is defined by P, we can predict the position and orientation. This is the orientation of the robot. By having this kind of configuration, we can put whatever our robot location, something like this, into a metric form here. And if we integrate, we can do this kind of thing. We can have a velocity relationship of our robot. So when we put the metric something like this, you can see that this is what happening in a real case. This is what happening in the robot. And when we have this thing, you can calculate the velocity of your robot in the x direction. So we have x and y direction here. So if we see here, if we have a movement here on the x direction, so means that you will have a velocity movement in this direction. And if you have a movement in the y direction here, means that you have a velocity movement in the y dot direction. And eventually you will have your what we call it, your Vx, your total generated velocity movement at this direction. So with that, we can break down our velocity relationship into two axes here. So you can see that we will have the velocity movement in the x direction, and we will have the velocity movement in the y direction, whereby you will have a total velocity, total combined velocity with respect to your robot heading. So this is your robot heading. Or if we expand it, we can derive this general kinematic motion of the differential drive mobile robots. So we know that when we have this kind of heading, when we have this kind of heading relationship, heading velocity, you can have the velocity and what we call it, you can have the velocity and orientation velocity of your robot. And also the kinematic of the mobile robot also can be written in terms of the Jacobian metric form. So you can see from here, we can represent the similar equation here. We can put it in something like this. We can rearrange into metric, and you can simplify it something like this. Why we want to simplify it later? Because normally when we want to do some control system analysis, some calculation of the motion, we will have this metric is easy to calculate using some tools inside the simulation. So that's why we need to arrange into this form. And if you see this relationship, you can see here on the general equation, and we simplified this equation on the bottom here. If we have a change in the theta, in our robot's motor motion, theta dot, we call it a theta dot, whereby we represent by q dot. And if we have a j here, this is the j, whereby the j is from the above here, you can predict what is happening to the position dot. So what is happening to the velocity, position velocity, means that you can predict this p dot here. So this is your p dot. So means that we can predict what is the velocity motion of the system. So if we can predict the velocity, if we want to see what is the location, so you can simply do the integration, right? So for example, I want to see what is my location in the x direction. I know already I have the x dot. So if I integrate my x dot with the dt, I can predict what is my x direction, what is my y direction. So by having this Jacobian metric representation. So this is how we do it. And this is some example of the differential drive motion. So this is if we try to load it into the simulation environment. So if you can see here, okay, this is one kind of robot whereby this robot have two wheels here, whereby each wheel is independent each other. And this robot also have the initial measurement unit sensor and odometer sensor, so that we can see and we can control it. So for example, on the terminal here, we try to give some command here, some cornering command. So you can see that this robot does not have a parallel motion. It has some trajectory motion, like the example you did in the Python. So the example like you did in the Python will have the same kind of curvature motion on the differential drive motion. So when we understand these properties, we can use some, for example, if you have this robot is moving, and if we understand the mathematical equation, we can take this robot dimension, and you can calculate it so that you can predict whether it has the same yaw rate, the same location, similar with the example or not. And by having this thing, you also can do the, if you're familiar with MATLAB here, you can do the calculation on the mathematical equation. So for example, if this is the example of the differential drive mathematical equation, the mathematic that I show to you. So if you see from here, we can have right wheel velocity, the acceleration of the right wheel, and also you will have a left wheel velocity and the acceleration of the left wheel. So we can predict, for example, on the left wheel, we give a higher speed, compared to the right wheel, we can play with it, and this is some normally some Jacobian metric, some mathematic equation that I show to you. So we can play around to see on how does our robot behave. So when we have this equation, we put into, for example, MATLAB, or if you don't want to use MATLAB, you can also do the same thing in Python. And we run our simulation. For example, you can see here the right wheel, the left wheel velocity is higher than the right wheel. You can see that on the simulation just now, it become the movement of the robot is turning to the right direction. So let's say we change it, the acceleration of the right wheel is higher compared to the here. So it change its movement from the right here to the left here. So because of the acceleration that we give on the right wheel. So this is the example if we use the differential motion, or you can do the same equation using the Ackermann modeling, the same equation. So what we can do is we put some Ackermann equation, mathematical equation inside the simulation model. So, and then we do the same, but of course the way the parameter will be different here. And if you see from here, there is d phi here. This phi is the yaw rate motion of our system. Means that we can predict the what we call it. We can predict the motion of our system. So let me try to skip a bit here. So you can see here, we can also simulate the motion of the Ackermann motion of our system, and you can change the parameter value here. And when you change the parameter value, you can also see how the Ackermann motion is a bit similar with the differential drive motion. So what we can see from this simulation, we can say that they are identical in terms of the motion movement, but different in terms of the mathematical modeling. So when we understand this mathematical modeling, you can predict this kind of thing. So means that you can do later when we do the control system, you can do the control system part. Okay, that is enough on the kinematic modeling of your system. And also, okay, this is a kinematic model of lateral vehicle motion. What is lateral vehicle motion? When you have, for example, this is your robot. The motion of the robot, this is the global axis. You will have the robot axis. For example, let's say I say that this is a X1 and this is the Y1. So means that your robot front direction is like this in the front direction. So normally when we create a robot, we want to create an autonomous robot. We want to create the robot that moves something like this, right? And if we want to create the robot that is moving something like this, we need to understand, for example, this is our road or our trajectory that we want to go. We want to understand what is the error in order to go to this road, whereby our objective is try to minimize this error so that when you create the control system, you can achieve a better control. So this kind of error, we call this as a lateral error. And in order to understand the lateral error, we need to understand the lateral vehicle motion. So that's why we need to develop some of the kinematic of the lateral vehicle motion, as you can see in the screen here. So this kinematic, sometimes we can call it a bicycle model, where we neglect some slippage or the vehicle itself. And we will have a bicycle model using the diagram here. We can use the same bicycle model, whereby the bicycle model will have some relationship between the body slip, what is happening if your vehicle have or robot have some body slip, and what is happening if you have a steering, configuration of your robot. And also, we can also consider the Ackermann turning geometry in order to understand the robot, and you can understand the geometry. And also, this is the summary of the kinematic model equation, whereby, for example, if we use vehicle slip angle, you can see that we have a lot of equation. From the previous kinematic, you have a general kinematic, but for this equation, the bicycle model, you have some equation that is considering the robot or the vehicle slip angle, so that we can estimate what is happening if we have some slip over here. And also, if we want to generate a motion at higher velocity of the robot, we need to consider a dynamic as well, because the force of the momentum of moment of inertia is involved inside our robot's configuration. So at higher speed, the assumption that velocity of each wheel in the direction can be no longer by is in this case, instead of the kinematic model, dynamic model for lateral vehicle motion must be developed. So we want to understand what is happening if we have a dynamic of our robot here. So you need to understand, if we take a cornering here, what is happening here, what is happening to our yaw rate, what is happening to our robot. So normally in this part, in the control system part, they have one topic they call is a state space model topic, whereby in the mobile robot, normally we use a bicycle model for Ackermann-like steering, so that you have a state space configuration. So this state space configuration is try to generate the behavior of our robot by having into this form. So what is meant by this form is if we have any, they call it plant. This is the in the control system terminology, they call it plant. But in simple word, this is your robot. So in simple word, inside here, this is your robot. So if, for example, if I'm giving my vehicle velocity at 100 km per hour, and I'm giving the steering angle is 20 degrees, right? In order to control my robot, means that my vehicle is traveling at 100 km per hour, whereby my steering of my vehicle is 20 degrees. What will be the output? What is the yaw rate? How does it move? What will be the position? Right. So this will become the output, whereby we can simulate what is happening. Inside here, inside this state space model is our robot parameter model. Means that you will put the mass of your robot, the friction coefficient, you will put a lot of the dynamic parameters inside here. So means that if we have a dynamic parameter inside this equation, and we put the input, the steering input, and the velocity set that we want, then you will be able to predict what will be the yaw rate motion of your system by having a state space model. So this is the example of the state space bicycle model that they have developed, the researchers have developed previously, whereby if you put this equation inside your system, you'll be able to predict these four things. You'll be able to predict the lateral motion, you'll be able to predict the yaw rate motion. So by having the state space configuration, of course, maybe some of you are not from the control system background, maybe this is a new thing for you, but don't be scared if you see a lot of mathematics equation. But what I want to emphasize is, by having the state space, by understanding the state space of your system, you'll be able to predict the motion. And we can also consider if, for example, if your robot is navigating at different terrain, right? For example, you have a road bank angle, means that this is my robot is something like this. So this is my tire. So if we have this kind of angle, we can consider it. So for example, in the agriculture, whereby your robot is navigating at an uneven terrain, whereby you have what we call it a road bank angle, and the road bank angle is always changing its value. So normally when we do in the experiment, in order to measure this inclination, we use accelerometer so that you can estimate the inclination angle of your robot. Using state space also, you can estimate what is happening to your robot if you consider this kind of rope bang angle. And when we develop this state space, we can expand the model by having understanding what is lateral error and what is orientation error. So the lateral error, as I said, is, for example, I have my target point, my road here. I want to go to the target here. So this is the E1. So this is my lateral error. What is my orientation error? So let's say this is my robot heading. So this is my robot heading angle 1. And this is my road heading in this direction. So if we put the road heading, you will have, this is your road heading is at here, heading 2 angle. So you can see that we have 2 different angle heading here between the H1 and H2, whereby this difference is called the orientation error. So if you minimize the E1, so if the E1 becoming 0, we can say that the robot will be located in our target trajectory. If the E2 is becoming 0, we can say that the robot follow the orientation of the system. Okay, so this is actually the simulation that you did in your Python in Anaconda previously. You have 3 simulations: move to pause, you have model predictive control, and you have another simulation. I don't remember what is the name. And these 3 simulation, if you see, for example, a Stanley, one more is Stanley controller. What the Stanley controller is doing is, I try to relate with the error with respect to road is, this is the target. For example, this is the target whereby the Stanley controller will have Aizzat point. And this is your robot. What is happening to the Stanley controller is, they give you one target point here. And whenever you have this target point here, the Stanley controller will help you to calculate what is the value of E1 here. And let's say this is your heading 2, and this is your robot heading. So the E2 can be obtained by H1 minus H2. So you can get your E2 here. So what is your E2? So it means that the Stanley controller will help you to calculate the E1 and E2, and they put it into the control system equation. The control system equation is giving the feedback to your robot so that they can move near here. So whenever your robot is reaching at here, at this location, next the Stanley controller will give the next target point. So you will have another error, and your robot try to follow this error. The Stanley give another, robot go, and eventually robot will follow the trajectory that we want. So this is what is happening when you are using the simulation that I gave to you last week. So there are 2 kinds of error that we need to understand: the distance error, lateral error, and the orientation error. So these 2 errors are the most important error when we want to develop an autonomous robot. Of course, there will be another error. For uneven train, maybe you have a roll rate error, this kind of thing. But the basic is these 2 errors that we have to understand first. And using this error, we can derive the equation here. Just see the slide. Yeah, they have some mathematical part here. And eventually we can relate the error here that we want with respect to the in the state space form. So we can generate a state space form here, so that when you have this state space form here, we can simulate the movement of our robot, the dynamic movement of our robot. And if we include the road bank error here, which is the sine theta here, you can see that the equation becoming something like this. And if you put this equation inside the Simulink, you can see that you can generate the movement of the robot. And in fact, you can do the state space simulation if you don't have MATLAB installed in your laptop. You can do the simulation of the state space in the Python as well. You can Google the Python toolbox, the state space Python toolbox. Then there will be a toolbox of the Python, and inside the Python toolbox they have A, B, C, D, so that you can put the metric of the equation inside here inside the Python, and then you will be able to generate the motion equation of your system. And this is the summary of the motion equation of robot. And do we have a detail about the dynamic motion in terms of the lateral? You can estimate the force motion using this equation, the body slip. And I don't want to go in detail in this equation, but I just show you an overview so that you see that what is happening if you go in detail on the mobile robot navigation. So you will see a lot of this equation. Although it seems complex, but it is necessary for us to really estimate the motion of our robot. So in summary, I have shown to you the kinematic and dynamics model of the robot. And in order to understand this model, more in-depth study, of course, every topic you will have a lot of analysis you have to do. So maybe I hope that the kinematic overview in the topic that I share to you is you are able to have some brief overview. You are able to understand what you are doing with the simulation in the last lecture. And a good understanding on how the model work will give us an idea on how will our robot perform during the experimental development. So when we want to design our robot, normally we will put it into our simulation platform first, and it will assist our control system development. So normally we don't strictly put our control system in our robot. We will try to simulate it, try to tune it, and after everything is ready, we will put it into our control system development. Okay, I'm going to change to new topic. Is there any question? I hope that you don't get confused with the equations.
Is there any question from students or also some of the lecturer here?
I think I just want to have some comments actually.
Okay.
Actually, the model student will have their lecture in modeling.
Okay.
In next semester, actually, it's
Okay.
also about
the student will understand that, will learn that.
They will have learn
good.
the state space model.
Oh, good.
Actually,
good.
in the modeling in biological and also.
Okay, good, very good.
Yeah.
So means that they can continue.
Pak Dimas, and also I teach the modeling actually.
Yeah, so means that they can use the same equation into the state space model, then they can proceed further. I think that's better for them.
Yeah, they can also try if in the practical assignment or.
Yeah. I agree. Oh, that is good. Okay. Yeah, because the state space is one chapter in control system as well, right? They need like several topics in the state space itself. So maybe I just give overview only. I don't go in detail in this lecture because of the time.
If they want to have in detail, I think they will take the modeling.
Yeah.
And I usually use MATLAB, but I think Pak Dimas use Python, I think.
Yes. I teach them Python.
There are some software that we introduce to our students.
Because I previously I tried to ask Dr. Dimas because I understand that not all student is using MATLAB, so that's why if Python, then we have no problem because it's open source, right? In Python also we can simulate the state space.
Yes. Okay. Thank you.
Okay, thank you, Doctor.
Okay, is there any other question from student? So that is why in the previous semester you learn basic mathematics, calculus 1, also in this semester, calculus 2.
You see, there's a lot of mathematics, right?
Yes, yeah, for engineering student, there should be a lot of mathematics, right?
Yeah. Hopefully
Okay.
you don't get scared when you see a lot of equation in my today's lecture. It's just an overview only.
Yes. Okay, maybe no question for now.
Okay, so I can proceed.
Yes.
Okay. So actually, I want to continue from the previous sharing on the case study that we developed in our system. If you see from the previous, we developed our lane tracking, right? Whereby the lane tracking is based on the previous topic, which is the what we call it sensor, right? From the image processing sensor. And next is I show to you that why the concept is very important, because by understanding the fundamental aspect, then you can create some ideas and you can create a small things like something that within the student's budget. And when you grab the concept and if you have more budget, you can expand your ideas. So this is, for example, when I did with my friends, with my lab mate, we want to create something big because of we already create many small things before, and we would like to try something that is really big. So we start with the brainstorming of the idea. So this is the brainstorming inside the lecture room in 2019. So we imagine that we want to create this kind of thing, and what is the sensor we want to use, where do we want to use it, where is the placement of the battery. So we put some very general sketch. I put this diagram is because this diagram is what it kickstarts for our. I can say that the big thing is start from a very small sketch only, and we put some automation for autonomous vehicle. And it's not just for the vehicle, actually it's just for any robot. You need to have a how many the level of automation, we call it a level of automation from level 0 until level 5. And if you want to generate the autonomous tractor for agriculture, your robot need to have at least level 3 or level 4. So this is which part of the autonomous architecture. If we have a level 5, is fully autonomous, means that your robot can adapt in any environment. Your robot can quickly relearn if they have a very dynamic environment. But a good case if level 3, if we can go for the autonomous system in level 3 or level 4. And this is what we do in our autonomous bus, and the project is still in progress also. We try to develop into different tasks, a specific task. Of course, in the first task, we develop the electrical, the sensor testing, the mechanical configuration setup, some driving and steering system. Means that on the task number 1, we try to target that the vehicle can move like a normal vehicle. So mechanical, electrical, some concept. And the task number 2, we try to target that they will have our vehicle will be at a level 2 autonomous system. Is that they will have some computer assisted system. We call it in the level 2 drive. We try to change it into the drive by wire and stay by wire, like in the video of the forklift that you see here. In the forklift, we change it into, instead of the mechanical steer, we change it, we put a motor here, and we can do a drive by wire for our forklift. So normally we will proceed with the task number 2. And the task number 3 is whereby you started to put your autonomous thing into your system. So this is the part where we put a mapping and some system configuration. And when in this part, in the task number 3, you can start to move around your autonomous robot, and you can start to collect the data, and you can fetch the data. You can do the system integration and simulation after you fetch this data. So this is the task number 3. And the last task is we need to have a first stage of autonomous testing in the state road. Okay, this task will take more time, because in order to create a very big system or a robust control system, you have to ensure everything is ready. Maybe you do one test, you fail, you repeat again, and you maybe if this task is fail, for example, in our case, we try to move, we see that they can try to have a regulation of the drive to have automated control of the speed, but because of we see that we have some jerking and the slippage on the encoder reading, we have to modify some of our mechanical constraint here, and then we go back to task 1, and then we jump back to task 4. So it will repeating until you perfect your system. So there will be a lot of failure during the development. Sometimes you feel that you want to give up or this kind of thing, but this is normal, especially for students. And in fact, if you start a very simple project, that your lecturer gives to you, right? So you will feel that, yeah, your short circuit and your controller burn. I think it's normal. In fact, we still have the same thing. Okay, so this is the task number 1. We try to do the mechanical configuration setup, the driving and steering system, and then we do the electrical management, we do the sensor testing. So we try to start with the selection of the driving system. In this case, the gearbox. So we select some how many watt, 20 kilowatt electric motor. And the first prototype we do is we have some problem with our gearbox, whereby there is a misalignment between coupling and differential gear, cause friction and wear. Although the robot, the bus can be moved, but because of not perfect alignment, maybe during the CAD design development, we don't really fit it well, and the robot can move, but you can see that there is friction and wear, and you can smell some very from the heat, the heat smell over here on the driving system. And because of that, we modify. We see this failure, we remove again, we use a second configuration. Right now, our bus can move, and the problem is this configuration is we use a bevel gear, but the problem is this bevel gear, this configuration contribute to a lot of noise. The bus can be moved, the electric bus can be moved, but when we drive it, you can see a very high noise inside the bus itself. So we don't want this, because it's not nice when we say electric, but we expect that the bus will be in very low noise. So this is not good configuration. So this drivetrain issues is very time consuming. So we stay at lab, we did a lot of analysis, and until 2 a.m. in the morning, in the early morning, and we try to call a lot of drivetrain engineers in our team to do some calculation to solve this drivetrain issue. So this is the part where you need to have a fundamental knowledge, so that we do some, you can see my student doing some calculation here, some mathematical, you can see that some dynamic kinematic calculation, you can see some calculation on the mirror here, because we really need to not repeating any failure that we made previously. So we did calculate some calculation in order to this is the dynamic calculation. Maybe you learn in dynamic. If so, we did some dynamic calculation to calculate what is the value of the thing that is required in order for us to move the bus here. And next, we change it into the configuration of the drivetrain. So we put in this configuration, we put the drivetrain, and this drivetrain, we eliminate the jerking. And previously, this drivetrain is configured based on our previous calculation that we calculate previously, and we have the configuration is better. It does not contribute to the noise because we use belting and tensioner, but we have insufficient torque. This thing move, but sometimes when during the first phase, it takes a lot of time to move the bus, and although the noise is lesser, but they still have noise and some overcurrent issues and cause a high controller spike in our bus. This is the drivetrain issues. And because of the issue, we decided to design our own gearbox. So this is our current gearbox that we designed. So this is and then we when we design our own gearbox in our driving system, and you can see, okay, this is inside this gearbox. This is inside this gearbox, and we put a and then inside here we put some liquid inside here, and then we seal it. The reason why we put some liquid is to avoid some tear and wear. And then when we put it, and alhamdulillah, this bus can have a good motion now. I don't know whether there will be any issue later on. And this is another configuration that we use when we want to modify the shuttle. The first configuration, this is on the steering and in the front of the bus. The first configuration is we use this electrical motor. We have some chain here, and this chain here will create the electric motor pump. And this is, of course, if you use chain, it works, but it contributes to a lot of noise. And because of that, we try to change into using a belting. So using belting, the torque here is reduced, and cause the bell, you have a slip in the bell control. Because of that, what we call it, when you understand the configuration, the Ackermann steering configuration, you have a drive and you have a steering. We want to control the steer angle. So if you want to control the steer angle, you have to ensure that the pump is working perfectly, so that you don't have any slip, so that you don't have any noise in the sensor reading because of this slippage. So this is our latest configuration. We are using an electric assist system. We call it EPAS, electric power assist system. So this EPAS, we are using our customized controller inside here, so that we will have a torque sensor. We can feedback a torque, and we can use it into our control system, so that we can simulate here. So here you can see that there is a steering here, but we don't use the steering. We feedback it directly to our control system computer. So with that, we solve the mechanical issue. And of course, when we want to develop something, you can see that we calculate on there is what is the current consumption between each of the computer inside our electrical management. So we try to calculate, and we try to see how long does our battery can last. So for example, in our configuration, the maximum our battery can last is about 1.6 hours. It's about less than 2 hours. Because of the battery constraint, this is our maximum. Not too long, but this is just for prototype. And we try to calculate the total power. So for example, if you have multiple computer inside your bus, you need to calculate what is the power drawn, what is the sensor drawn. You need to calculate everything, and from that you need to calculate the total power required by your bus. For example, you have rotary encoder, you have IMU, and you have some inverter. And of course, we need to design our electrical power management. You need to have some circuit line connecting to the computer, electrical power management, and some sensor line, what is the voltage that you require. And you need to have your battery management system. For example, we use the battery, and you need to have, either when we buy the battery, it comes with a battery management system. If not, then we need to buy separate battery management system to regulate the battery. In this case, we customize it so that we can display using some display or some LCD. And after that, we use the sensor testing. So if you see from here, we put our LiDAR inside here, whereby we try to simulate, because during this initial testing, the bus is not yet fabricated. So when we want to fabricate the bus, we have to know the exact location of the sensor that we want to place. So in this part, we try to calibrate LiDAR and camera for our bus. And after we calibrate using a normal LiDAR, so we can have an exact dimension where do we want to put our LiDAR here. So and some location placement of our sensor. So when the shutter is not yet finished, we try to do some, if you can see the wire here, we put some actual connection that we want, and we try to drive this bus in a frame so that we see that is there any problem or not. So this is some pictures on the frame fabrication process that we develop, and after that we install the battery and we test the battery whether it work or not. Then it comes to the body fabrication. We as engineer, I'm not sure, I'm not good at designing, so we pass it to other designer to design so that the concept look futuristic of the system. So when they give us the concept design and we fabricate it. So our part is, we did, for engineers part, we did only the mechanical design, the electrical and the software, but the design we leave it to another expert. So this is the finishing. We use a lot of maybe some of the components, some of the body here, we don't use a real automotive grade body because this is just a prototype only. So we can see here that we have a location for sensor here. We put, and later we will install it with sensor. This is inside the interior. For example, the interior design, you can see that we have a U-shaped motion here with no steering. But the way we configure the configuration is you can open the seat here and you can pull out the computer so that if we want to debug something, we can do this kind of thing. And we try to obtain some futuristic concept, like in the monorail, you can see that there is a sliding door to on off the bus here. We try to put this thing, and when we involve a lot of complex thing, we forgot one single thing. When we design the sliding door, we face the experience is we forgot to put the emergency exit. So when the battery is running out, when we are inside, we are trapped inside, because there is no mechanism to turn to open the door. So because of that, we forgot, and then we have to redo it, the mechanical inside here, to put the emergency switch if we have power off. And we finish with installation of the sensor here, you can see, and sensor at the back here, but we don't put a case here. And this is our first trial here. From the slide, you can see from our first trial, when we want to move this bus here, you can see that there is a jerking here because the control system at the drive is not well optimized. We have a problem in terms of getting the right tuning value of the control system. And we try to see what is inside during the prototype development. What is happening is we have one computer here to measure the current and to measure the jerking, what is happening, to measure the jerking if we have any problem during the testing here. And of course, it happened many times that our bus is broken because of some current issues, some mechanical issues that we have to repeat again. It's not like a sweet journey at all. And after that, and when we finish develop the mechanical, we try to develop the drive-by-wire. So you can see from here that we try to control the speed at the back, and we can remote control the front steering here. So this is we can control it, and after that we can give a command to our computer to control the steering motion. So we give a command to control the steering motion, and we can integrate it with, for example, you can see there is a gaming controller here. There is no mechanical linkage at all. from the gaming controller, we can create a control system to follow the instruction of the steering here so that the tire can move to our desired connection. And we did some verification of the test case study. We tried to control it. You can see that this guy is controlling through remote control. There is no steering here. We tried to move around the campus to see, and we tried to do parking. You see there is no side mirror here. So what we can do is we go out and you can do the parking by using a remote control only. And after that, we did some mapping and localization using some mapping technique. We install some sensors and we develop our own customized IMU from here. You can see in the LiDAR connection here. And we did some calibration. And the first is we test it inside this room. So from the slide here, you can see that we see that there is a calibration, the LiDAR inside the room, and we test it in the car and in our simulation. So in our simulator that we developed, we put some camera sensor. You can see some raining simulation here. There is a raining, and we have a LiDAR so that we can do some offline data mapping. And we set up and we try to create some map on the our campus and our faculty. We try to create a motion, and this is the first example if we do the sensor fusion. If you remember a previous topic, I did talk about a sensor fusion, and I did show a very small robot doing. So we did on the bus using the same concept. So we did a sensor fusion. We fused between the odometer and initial measurement unit to create motion of our vehicle here. And you can see that there is a biasing. Actually, we move here, but you can see there is an error when we put some map inside here. And we did some error analysis inside the campus, and we fused with LiDAR, and we did some compression. So this is example on when we do a 3D mapping. So you can see how our bus see is the white color here. The white color is the mapping that we generate from the motion of our system. The colorful color here is the one that is being scanned by the sensor. So the red color is the trajectory motion. It's the same trajectory like you did in the simulation part. So when we do this is called SLAM, simultaneous localization and mapping. So this is the fast video. So you can see that we generate the trajectory in the red color. The scan is the color. So whenever you create a motion in the colorful color, you can scan and you can generate a map inside your vehicle system. So this is the map that you are going to generate. And eventually you can generate one complete map. So means that this map will be going inside your vehicle so that when we want to generate the trajectory later on, we can define where is the road that our vehicle can go, and we can do a control system and we can do a planning. So this is some mapping result, and this mapping we convert it into the binary format to reduce some data. So if you compare again with the map that we have, you can see that it no longer have a biasing error. It's exactly overlay with an actual map in our campus. And this is the example of the map that is being loaded when we move the vehicle. You can see that we develop the map can precisely have some, you can see that there's a 3D like a tree. There's a road over here. Maybe I fast forward a bit. There is a road over here that you can see the vehicle is moving. So this is the vehicle's current location here is moving. Whenever it moves, that it tries to continue to update the map. And this is some example on, this is some example on how we do the testing, the navigation testing. After we did some mapping, and when everything is ready, we try to do some sharp turning on our bus, and we try to do some uphill tests to see whether our bus can take some bumping or not, because we have to ensure that it is robust. And this is the video that is showing. Try to take, it's a very slow video. Try to take the uphill test, see whether it has any problem or not. And we try to do or to verify the turning, whether it produces the yaw rate, or we can estimate the yaw rate of the turning or not based on the steering angle. So this is what we do. We do some turning test here. And yeah, we do some, you can see the video, just some random maneuver to see. And we do the load testing. You can see many people inside the bus. We try to see what is the maximum value. So if you can see from here, that's all. I think the sharing about the bus and some kinematic, you see that when we want to develop some autonomous robot, there is a lot of things, especially for complex system, that we have to consider. And each system is dependent to each other. So if we focus more on the software, but we neglect the mechanical parts, right? You can see that if the failure on the mechanical part, we cannot proceed with the software, although we have a very good software. But if we have a very good mechanical, but the software is lousy, then we have a problem. So with that, I end my lecture here. My last session here with yeah, so you can ask any question if you want. Thank you.
Thank you very much, Dr. Aizzat. Very nice lecture.
Okay, thank you very much.
Dr. Aizzat,
Okay.
before I let any other audience ask, I would
Okay.
like to ask about I'm very interested for example this one. Currently you're still developing this autonomous car?
Yes, we are still developing because this is like a long-term project. If we don't plan, we did not plan actually to sell it, because we are not a company. So we try to, because when we develop something from scratch, we learn a lot of things. And
yes.
We are also in progress in developing you see the video here, the autonomous forklift as well. The forklifts, yeah, this is my two ongoing project. So the reason is we try to see what is the actual issue. And then after that, we collaborate with the actual autonomous company in Malaysia, the industry, which is my supervisor as well. So that when we develop something that because the company, they don't have a lot of funding, they don't have a lot of time for R&D, right? They need to commercialize, they need to sell in order to survive. So from our part, we try to provide as much information on the R&D perspective in order to improve their system. And if you see, for example, we have I did show you the IMU. You can see in this slide here, this is the IMU. You can see that this is just a 3D printed IMU only. It's our own developed IMU, whereby we collaborate with a local company to develop, they fabricate the IMU, and we did the calibration part. Because the industrial IMU is very expensive, right? So we try to reduce the cost. So we develop, we customize it, and we tune it. So this kind of thing.
How many lecturer and student in this project?
In this project, we have 5 active lecturers, one project leader, and four is doing the technical work. We have mine is more on the SLAM, on the system integration. We have another lecturer doing the steering, stable wire system, is doing by another lecturer, and one lecturer, one engineer is working on the for example, if we have problem with the drive shaft, right, with the axle, so they did some fabrication. So it's different from different expertise actually.
That's nice. How about the student?
The student is actually, previously we have 5 postgraduate students in the initial funding. And because of the limited funding, right now we reduce until only 2 only. You see that the most of the impressive work is done by these 2 students.
Undergrad or postgrad?
Postgraduate, but we do have taken some student coming to internship in our lab, and undergrad also. For example, I have my FRP student. I will give some small project to this final year project students so that they can assist my 2 postgrad students. So the brain is coming from these 2 postgrad, but it's assisted by the class assignment, this kind of thing.
Nice.
Yeah, this is how we survive.
Okay, thank you very much.
Okay.
Is there any question? Because this is your last chance. Not last chance, but this is last class for
Yeah.
Dr. Aizzat. So if you have any question, please, you can ask it. We have still 10 minutes. You can also ask in Indonesian.
Yeah, no problem. I can understand.
Okay.
Actually, if we are actually, I plan to add one more topic, which is but because of there is not enough lecture, maybe in the session, whereby I'm going to share a bit later if we have chance that what is the software required for, because I don't touch in terms of the software that we need to use for the autonomous system, this kind of thing. I think this part also important, but because normally this part it requires a lot of hands-on, so I'm not sure how to do it in online.
If you don't mind, we would like to add one, like what is that? Like online guest lecture, not outside of the class. If you don't mind, maybe we can add one topics, but it is not compulsory for all students, but if they are interested, they can join. Something like that. I will talk to you later.
Okay, no problem with that. Yeah, this maybe this is just of the general overview, so that when the student want to go to something, they have some. Yeah, it's an optional in terms of software, right? It's a matter of preference. For example, some researchers, some students, they prefer MATLAB, some prefer Python, right? Some prefer Visual Basic. So maybe I would like to share from our experience what kind of software we use, so that they have some general overview on what they are going to do, something this kind of thing.
Yes, as you may have already known that I told you that we also start to some project for autonomous tractor here. And we start this year, and from these participants, maybe 2 students will help this project, and maybe we cannot achieve so much in this year. Maybe, but
it's okay.
We will try to start the project this year.
Yeah, because from our side also, we don't want to play outside by thinking about how do we make this thing is commercialized, because you see here the autonomous system is very expensive, right? And our country also is not ready for that. But the most important part that we see is if we understand the technology behind it, if how we use it in order to improve like our syllabus and to train so that our student is capable for future technology. This is our main objective is actually.
Yes, I agree with that. Okay, is there any question? Pak Darmanto, Pak Ubaid, or any students? Don't be afraid of the mathematics equation there.
Okay, maybe I would like to add one more thing about student, Dr. Dimas. I'm going to post in the Google Classroom the Google form whereby they need to put their full name and the student ID. I will issue some participation certificate for them that they're attending this class, and then maybe you will pass to them. And I will put one more, the last assessment, maybe within 1 week from today's lecture, for that they upload some understanding about the simulation they had done and some relation with the last lecture, so that you can assess if you want. I think that's all from me.
Okay, thank you very much, Dr. Aizzat. Really, there are no other questions? No question?
Very shy.
Yeah. You know, before the midterm, they learn about Laplace transform and also and also mathematical modeling, but maybe it should be at your part. This is how to apply the application.
So
right?
this is the application. Maybe you share the concept. So it's good. If they can relate this thing.
Okay, if there are no questions, then I would like to thank you very much for Dr. Aizzat for these 3 lecture. I think the control system and automatization courses this semester is very special, since we get a lot of new knowledge and insight from industrial speaker and also overseas speaker like Dr. Aizzat. We will use what we have got this semester to update our syllabus and curriculum, and also we will start the project, and I hope that some students also will join us. For the previous lecture, door prize I've already sent to the winner, and then we still have assessment from Dr. Aizzat, and I expect one more guest lecture for Dr. Aizzat about for all of you that interested and want to know more about this topic, then you can join the guest lecture. I will inform, make the poster later. That's all. Just keep update on your Google Classroom for the assignment and last assessment from Dr. Aizzat. Thank you very much. Maybe we have you. I hope that we can take the picture together. Okay. If you have, if you can turn on your camera, please turn on your camera for all students and lecturers.
All pictures, screenshot.
Screenshot. Because this is the last class. Okay. Wait. Okay, the first slide.
You want to do like a great screenshot or what?
Yeah. Okay, first slide. I will take the picture. Oh, wait.
Can you send it to me also later, Dr. Dimas?
Yeah? Yes, I will send to you. Okay.
Good.
Okay, first slide. Okay, second slide. Oh, this is manual. Okay, there are 8 slides.
Wow, too many students. I have too many Indonesian students.
Maybe student can help also make a screenshot.
Yeah. Please. Okay. Not all turn on the camera, so fourth slide is already the final slide. Okay, I think it is enough. Okay. Thank you very much for everyone participating in this lecture. Then I hope this lecture will give you benefit to the fullest, and then we will see you. I will see you again on next semester for other lecturer, other classes, and some of you maybe. I hope that can work together with Dr. Aizzat later, and also with me. Thank you very much. Have a good day. Wassalamualaikum warahmatullahi wabarakatuh.
Bye bye.
Salam.
See you.
Bye. Thank you very
See
much.
you.
Waalaikumsalam.